Okay, excellent. So my name is Manuel Martínez from the University of Valencia, and following with some of the topics represented by Professor Javidi, I'm going to speak about the connection between the plenoptic camera and the flat integral imaging display. So let me go a little bit to the beginning of the concept, and to say that conventional photography camera, they do not have the ability of recording three-dimensional information of three-dimensional scenes, because they don't have the ability of recording the angular information carried out by rays of light passing through the objective. Instead, the irradiance received by any pixel is proportional by the integral of all the radiance carried by all the rays. So angular information is missed in conventional photography, in conventional imaging. So if we want to make three-dimensional imaging, we need to record, we need to collect the angular and the spatial information, both. Then much more interesting would be a system with the capacity of registering a radiance map with the spatial and the angular information of all the rays proceeding from the scene. This map is well known as a radiance map, or also integral photography, integral image, light field map, or plenoptic map. So many names, many people working in the same topic, but under different perspective. So the first and a very clever way of recording the plenoptic map produced by 3D scenes was reported more than 1 century ago by Liebman, who proposed something like the scheme I'm showing here. He proposed the integral photography, which is based in inserting a microlens array in front of a photographic film. In this way, it is possible to record in the film the information of many rays, the spatial information and the angular information, so the place where the rays impact the microlens array and the angulus of these rays. And this can be represented in a plenoptic map. Then we have a spatial information in vertical, in columns, and angular information in rows. Another way, much more recent, of recording the plenoptic map of three-dimensional scene is the plenoptic camera. A plenoptic camera, I'm showing here the scheme, is in some way a very efficient way of recording the plenoptic map, because it is made through a monocular camera, conventional photographic camera, in which it is inserted a microlens array at the plane of the image, and the sensor is displaced axially till the backfocal plane of the microlenses. In such a way, every microlens is collecting a single spatial position but many angular positions, and this information can be represented also here in a plenoptic map. The main advantage of plenoptic camera over the original Liebman design is that with a plenoptic camera we are recording a collection of microimages which are ready to be directly projected into an integral imaging monitor to produce auto-stereoscopic images. So this is because the image of the 3D scene produced by the camera lens is in the neighborhood of the microlens array, with some parts in front and some parts behind. So I'm going to show you how to use the information obtained with a plenoptic camera. So this is a scheme of a plenoptic camera that we mounted in our lab. So this is the camera lens, the microlens array, this is the three-dimensional scene, and this is, a photographic camera by which we collect the micro-images obtained at the backfocal plane of the microlens array. So this is an example of the micro-images we obtain. You can see that any micro-image is not a circular pixel, but it is a kind of circular microfield in which there is a lot of angular information. If we put this microimage in a display, in a monitor, for example, a tablet, because it's high-resolution monitor, and we place just on top of the tablet a microlens array similar to the one used in the collection, we can see that we are projecting three-dimensional images with continuous parallax. I am showing here the horizontal parallax, but all these images have also vertical parallax. Here I'm showing you a second example of the kind of three-dimensional images that can be projected in an integral imaging monitor. So with a plenoptic camera, we can capture the microimages that can be projected directly onto the integral imaging monitor. But the main problem of the plenoptic camera, which is based in the use of a conventional photographic camera with a microlens array at the sensor plane, is that the parallax is very low, because the parallax is determined by the size of the aperture stop of the camera, which is usually about 1 centimeter or less. So parallax is very low. But to solve this problem, we can note that, in fact, the information that we are collecting with a plenoptic camera is the same as the information that can be collected with an integral imaging device like the one designed by Littmann, but rotated 90 degrees. So we interchange rows with columns. So it means that if we take the micro images of the plenoptic camera and make some kind of pixel mapping, we can build a collection of elemental images, each one with a different perspective of the original scene. So, and this is very good, because we can collect a collection of elemental images not with a microlens array, but with an array of digital camera, or with a single camera which is translated or moved in a motorized rail. And therefore, depending on the way we crop these elemental images, we can change many things in the images that we will project in the integral imaging monitor. So we can see here that there are different ways of cropping. Then I show you, for example, let us suppose that I take 5 by 5 elemental images of the three-dimensional scene, each one from a different perspective. I have one free parameter. The free parameter is the cropping parameter. So we can crop these images in a different with a different factor. So then we crop the images. We obtain the collection of elemental images. Now we extract the pixels, or it means that we can make the transposition between elemental images and micro images, something that way. Or with a different level of cropping, we can obtain another different collection of micro images. So, with an array of digital camera, we can obtain elemental images with high parallax, and we can calculate from these elemental images with high parallax, we can calculate the corresponding micro images, similar to the ones obtained with a plenoptic camera with high parallax. And then we can directly project these micro images onto our integral imaging monitor. So, so you can see here that this is the microlens array. It's a microlens array with a pitch of 1 millimeter. Here is a microlens array. So we project the previous images in the iPad, and then we place on top the microlens array, and you can see that we can be displaying three-dimensional images with different field of view, depending on the cropping we have performed onto the elemental images. So we can make many things with the information obtained. We can make even kind of traveling. We can follow different parts of the scene. And to finish with my talk, let me show you. This is a picture of our lab. Here in the middle, we have a big integral imaging monitor in which we have a high-resolution screen and a big microlens array, and then we can project there some images obtained with our device. I can show you the result. So we can project images in which there are some parts in front of the monitor. You can touch them. There are some parts behind the monitor. All of them are obtained with very good parallax and a very good viewing angle. And okay, so with this I finish my talk. Thank you very much.